Hello, everybody. This is the cryptography introduction talk on the browser track. There was a similar talk to this one yesterday on the Chrome OS track. That one was a very traditional introduction to cryptography. And this one is a little bit different because we didn't want to duplicate things completely. So if you do want a more standard introduction, do go look for that video from yesterday afternoon. This one, I'll be giving an unabashedly more modern perspective, and some of the terminology will be different. So the one yesterday will fit in better if you are very much coming from the beginnings and you want something that meshes more with other resources that you'll find online. Whereas today's talk is a slightly different spin on things. But here we go. So cryptography is a large topic. And there are many parts of it that are fascinating, and I strongly recommend that you go explore them at some point. From the complexity theory and interactive proofs to private information retrieval. But today we've only got 45 minutes, so we're going to be focusing on the bread and butter of cryptography: message confidentiality and authenticity, and not even some of the fancy patterns of this, just the very common ones. But this is 99% of what we do with cryptography. So defining terms, I just said message confidentiality and authenticity. What does that mean? So for the purposes of this talk at least, and I think in general, confidentiality means that only the intended recipient of a message can read it. And authenticity simply means the message came from the intended sender, has not been altered. So those are the two properties that we're going to try and provide. And obviously, when you are talking over the internet or over Wi-Fi, these are desirable properties to have. We do not believe that our wide-scale networks are especially trustworthy. There are many parties that could watch things or could manipulate things. And so we want to avoid those concerns with the use of cryptography. So what does cryptography give us? The way to think about what cryptography provides in this context is that it gives you some very useful tools, but it's important to note that it doesn't solve the problem. It doesn't make the problem go away, but in a couple of ways, it transforms it in very useful ways. The first way in which it transforms the problem is that we can extract the confidentiality and integrity of a large message into a much, much smaller key. And this key may be 128 or 256 bits long, but in some sense, it contains all the confidentiality and integrity of the original message. And so the first pattern we'll see is that we can take a message and combine it with a key and produce what here is called a sealed message. And you'll note the sealed message is slightly longer than the message. It has a little blue bit at the bottom. We'll get back to that in the future. But if you can confidentially transmit the key, which might be small enough to read out over the phone or write on a piece of paper, then the confidentiality of the potentially much larger message is assured. So that's a useful trick in that it makes the problem much smaller. So that's the first pattern. And the second pattern is more powerful, which is that it allows the key and the message to be separated in time. So if today you can authentically transfer the key, then tomorrow or next week, you can send the message. And you can leverage the confidential channel that you have today into the future. So as an example of how we might use this, if you go and buy a Chromebook today, we assume it comes with an authentic copy of Chrome OS. And that contains keys that are then used to establish confidential and authentic channels to Google as needed in the future. So the trusted exchange there was when you purchased the Chromebook. And cryptography lets us leverage that trusted exchange into the future because we can move these properties around in time. So with that in mind, it's worth just repeating that cryptography is providing you tools to transform these problems in hopefully useful ways, but you're not solving the problem. When you hear in the news that some data breach has occurred, but the party in question says it's okay because the data was encrypted, which is also something that has been codified into some laws, it should be clear that that is not an answer, right? Simply stating that the tools have been used begs the question of how they have been used. You have to understand sort of how the encryption has been performed and how the keys are managed in order for like it's encrypted to be a meaningful answer. So today we're going to cover some patterns of encryption, some patterns of how we want to do message confidentiality and integrity. And I'm going to break it into three. The first of these is one-to-one. So message exchange between exactly two parties. And in parentheses in this talk, I will give the more traditional terminology for some of the things I'm talking about, which will help you link it with other resources you can find on the internet. But throughout the talk, I'm going to try and use the terminology here, just in the hopes that it is perhaps a more intuitive way of thinking about it. So next, many-to-one. Many senders might want to send messages to a single receiver. Now, when you have many parties transmitting to one place, the integrity, the authenticity of the messages is less pertinent because you don't have strong identity for the senders, but you want to ensure confidentiality. And then the last pattern is one-to-many, one source of messages sending out to many receivers. And here we have the opposite. Integrity is what is important here, whereas confidentiality is much less clear how that would apply here when you are sending it out to so many people. Like there is a phrase that you can't keep a secret with 3 people. Well, when you have many people, confidentiality seems immaterial. So to make these more concrete, let's discuss some patterns of how these are used in Chromium. So for one-to-one encryption, the first example here is encrypted incognito profiles. When we have an incognito profile, we want the information in it to be transient. But for example, on Android, that can be a challenge. If we want information to be transient, we want to keep it in memory, but memory is a limited resource. And if another app is coming to the foreground, we might not have that amount of memory to be able to store it. So how do we solve this? So we use the fact that I mentioned that cryptography lets you squeeze down the confidentiality of a message into a small key. And so we could write out the profile data to disk, which would typically risk the confidentiality of it. But we could use one-to-one encryption to communicate with ourselves in some sense, with our future selves. And so the confidentiality is kept in memory in a small key, whereas the message can be safely written out to disk for when we come back into the foreground and need it in the future. Other examples of one-to-one encryption, password-based encryption, which we will not cover today. If you want to do password-based encryption, seek advice. There are a number of times in this talk where I will simply say seek advice, which is a pointer that something is subtle. But we do this in Chromium. And one-to-one encryption is a component of many-to-one systems, and we will cover that later in the talk. So many-to-one, many senders sending confidential messages to one place. So when Chromium is uploading metrics, we want to ensure that these metrics are confidentially exchanged with Google, but there are many instances of Chromium running in the world. Web push is another example. If you go read the RFC on that, you'll see how it uses many-to-one encryption to ensure confidentiality through the push provider. And then one-to-many integrity software updates are the common example of this and an absolutely critical one. Updates are signed, and that is how we ensure that they are authentically coming from, well, from Google, or in the case of Chromium, from the browser provider. So dealing first with one-to-one encryption, here is the model I presented previously. In some sense, this process combines a message and a key and gives you a sealed message that is slightly longer. Now, the sealed message has to be slightly longer. And the reason is that if every possible sealed message was valid, then we could never reject forgeries. So if we did not make it any longer, we could not possibly encode every possible input message into a sealed message of the same length without every sealed message potentially being valid. So we have to make the message longer so that the number of valid messages is minuscule compared to the total number of messages. We're going to discuss some of the properties of one-to-one encryption, but in order to well ground that, we're going to need to dive a little bit into how it works. And in the interests of time, this, as with so much in this talk, is a simplification, but it's not too far off what is commonly done. So the way in which we seal messages, firstly, we take the key that is provided and we elaborate it into a nearly infinitely long, random looking series of ones and zeros. And for every 1 and 0 in the input message, where there is a 1 in this nearly infinite stream, we flip the bit in the input message. And that is XOR. And you can take my word for it for the moment. What that produces is an indistinguishably random output. You might want to think about that and prove to yourself that you believe it's true, but that is how we do it. And again, in parentheses at the bottom here, I have a couple of terminology references that you may have heard, AES counter mode and cha-cha-20. So going back a slide, when we transform the yellow message here into the green sealed message, this is what we're doing. And obviously this is length preserving, so we haven't expanded the message yet. In order to expand it, and the details here are not important, so I'm going to brush over them quickly. We take the green, right, the sealed message, we break it into chunks. We interpret each of those chunks as a number, and those numbers become coefficients in a polynomial, which we evaluate at as a separate key, in fact, and then we add in a third key. Now, it is possible that these different keys could be taken from different parts of the input key, but it's much more common that the one-to-one encryption method has its own practice for elaborating the input key into the various subkeys that it needs, the details of which we don't need to go into here. Again, terminology references, you can find this in the world as Ghash or Poly 1305. But this produces what here I'm calling the tag in blue, which is the bit that we've stuck on the bottom of the sealed message here. So with these details in mind, you should have enough understanding to motivate the following few slides where we discuss some of the challenges. So as an example, imagine that we are using a one-to-one method to produce sealed messages, and the service answers a series of yes and no responses. And I mean literally the ASCII string yes and no. So the first thing to note is that if you encrypt a series of yes and no messages, well, yes is longer than no. The overhead, like the blue tag that we add, is a fixed length, typically 16 bytes. And so every yes reply is going to be 3 plus 16, 19 bytes long, and every no reply is going to be 18 bytes long. And so all the confidentiality has been lost. So it is very important to keep in mind that message length is not hidden. This is pertinent in the real world. Papers have shown that if you analyze the traffic patterns of an HTTPS connection, you can tell some things about what is going on. Different parts of a website elicit different patterns of traffic, and there is some information leakage there. In this particular example, I have concocted something where all the information is leaked through the message lengths, which is an extreme case. If you want to deal with this, then padding up to a fixed maximum message length works. That is a solution. There are also more complicated padding patterns, but they are also more complicated to analyze. If you think you are, if you are unsure about message padding, seek advice. So we augment our example service to say, rather than encrypting yes and no, we will encrypt yay and nay. The advantage of that being yay and nay are the same length. So we have solved the previous problem. But our next problem is, as I've described this, the encryption is deterministic. Each encryption of yay will map to one sealed message, and each encryption of nay will map to a distinct sealed message, but there'll only be two possible sealed messages. So someone who can observe these messages going past, they don't know which is which, but they know the pattern. And if they ever discover what any one of them was, then they know everything. So that doesn't seem very good. So clearly what we need is for this one-to-one sealing process to be non-deterministic. It needs to produce different sealed messages every time we attempt to seal the same message with the same key. Rather than actually making the process non-deterministic, which makes testing more complicated and a number of other things, the non-determinism is pulled out into a value that we call a nonce. So we are updating our conceptual model of this one-to-one encryption to include a new input, this purple nonce. And nonce here means number used once. So even though our message may be yay or nay repeatedly, and our key is the same, our nonce varies, and that causes the sealed messages to vary for each input. So we've solved this problem, but this is subtle, and it's very important to note the next requirement. The pair of a key and nonce must never be repeated for two different input messages. If you have a random key that you only ever use to seal one message, then your nonce can be fixed because the pair key nonce will be unique. But if you use the same key multiple times, the nonce must be different for every single distinct input message. There are two ways realistically to achieve this. Firstly, your nonce can be a counter. If that is trivially possible to do, that you have a single encryptor that can keep state, your nonce can just be 0, 1, 2, 3, 4. The nonce does not have to be random. It simply has to be unique. That distinguishes it from an IV, an initialization vector, which you might see in some other parts of cryptography. If you cannot trivially implement a counter, then you can generate the nonce at random. But this receiving side must know the nonce for every message. If it's a counter and you have a reliable channel, then that's implicit. It's just the message number. If it's random, then you'll have to include the nonce with the message. Nonces are typically 96 bits long. And the canonical standard and accepted limit for how many random values you can generate before the probability of collision is too high is 2 to the 32. It is the length in bits minus 32 divided by 2. And for 96, minus 32 gives us 64, and divided by 2 is 32. So at most 2 to the 32 random nonces per key. If you are even close to hitting that, seek advice. I'd also note that nonce duplication leads to the collapse of security in many cases, not just that the system degenerates into a deterministic scheme. To consider why, think about going back to this slide. If the key and the nonce are the same, then this pattern in red will be the same every time. And if you have two distinct messages that have been XORed with the same pattern, you can XOR them together, and what you get is the XOR of the two input messages. So if you know any part of one of those messages, then you know the other part. Also, and I'm going to skim over this, if you repeat the nonce, attackers can observe this polynomial and start to solve it. And so very quickly, you lose authenticity as well. So it is extremely important to keep this nonce uniqueness requirement in mind. Finally, we now have a service that is encrypting fixed length messages, and it is using unique nonces. And so there is no observable pattern in the output messages. But an attacker might still reorder the messages. They might put them in contexts that are unexpected. So In addition to the pattern that we showed before, adding the nonce, we're going to add one last input, the blue additional data here. This lets you bind in any additional context you require. It is not transmitted. It simply needs to be equal at both the sending and the receiving side. So perhaps you can ensure sequencing by having a counter nonce, and that's fine. But if not, the additional data is somewhere where you could put a counter. It's where you can put flags like end of stream, any information that needs to be authenticated. And it is important to consider how your messages could be lifted into a different context and then misinterpreted by a receiver. But this is now complete. This is our model of one-to-one encryption. And to make it concrete, if you are in Chromium, this is how you would use it. The header is aead.h, and I'm going to show some snippets from the beginning here. Here is a list of concrete algorithms. AES-GCM is by far the most common, but there are also other options. If unsure, again, I'm going to say seek advice. But very briefly, SIV mode lets many more messages be encrypted for a given key and is mostly resilient to nonce duplication. And CHA-20 Poly 1305 is much faster when AES-GCM support is not available in hardware, although that is a diminishing series of cases when Chromium is concerned. The actual functions, this should not be a surprise if you keep in mind the diagram that we have built up. The inputs are the ones that we had in the diagram. Sealing seals the message, open opens the same. Obviously, open can fail, whereas seal always works. The next point to consider is seal and open, the APIs just outlined, are one shot, in that there is no streaming. You need the complete input message before you can produce output. Consider this next line, which is something you'll see quite commonly suggested online. So GPG is a command line tool, and in this particular mode, it's being used to do one-to-one encryption. And its output is being piped straight into tar, which is like unzip. So GPG here, unfortunately, releases the prefix of the message before it has authenticated the whole message. If you recall, when we expanded the sealed message, the tag was put at the end, and you need the whole message in order to know whether that tag was correct. So if somebody did this pipeline, the message could be altered, and that's bad. So the bad output could be sent into tar, which will act on it and mutate the file system before we know whether it is in fact authenticated. And this is called the release of unauthenticated plaintext. Because this is such a sharp edge, our APIs do not allow this. Now, there is obviously the question of, well, what do you do when the message is huge? And I wish there was an easy dominant standard for how to turn a one-shot system into a safe streaming system, but unfortunately not. So this is another point where I say, seek advice if you need to do this, but don't do what GPG is doing here. Next, in the many-to-one pattern. So this is many senders sending confidential messages to a single receiver. And if you recall, the example I gave here was something like, I think, metrics upload. So in many-to-one and one-to-many, it is the case that there is no longer a single key, because our parties here are identified by the keys that they hold. And if there was a single key, there would be no distinction between the many and the one. There would simply be a big pile of many. So in order for there to be many and for there to be one, there are two different keys. The key for the many, we call a public key, and the key for the one is the private key. So in many-to-one encryption, the message that we send is always itself a one-to-one key. Remember, we said that a one-to-one key is simply 128 or 256 random bits. So we will always, in a many-to-one system, leverage a one-to-one system. and we will bootstrap it by protecting its key in the many-to-one pattern. Let me go over that in more detail. So here is the pattern of many-to-one confidentiality. Our input is a public key, and what comes out is an encrypted message and the one-to-one key that is encoded inside that encrypted message. The encrypted message we need to send to the counterparty, the one. The one-to-one key we hold, and we use it to then use in a one-to-one encryption system to send the much larger, meaningful message that we in fact want to send. And again, in parentheses, I've referenced some standard terminology for this that you might see elsewhere. The important point to note here is that the one-to-one key is an output of this process. In traditional public key encryption schemes, the one-to-one key is an input. But since it's just a random string, it doesn't really matter whether it's an input or an output, because a random string is just as good as any other random string. But that makes it sound like this is a trivial change, but it is not. By having the one-to-one key be an output of this process, it allows a huge degree of simplification and robustness. And had we understood this 30 years ago, we would have avoided a lot of problems. So if you are familiar with, say, RSA public key encryption, that is a traditional scheme where you pass in the one-to-one key that you want to be encrypted. And that has caused a great deal of problems. The correct way to use RSA is RSA Chem, where Chem stands for Key Encapsulation Mechanism, which is what I'm describing here is the standard terminology for it. But unfortunately, this concept that the one-to-one key should be an output came too late for RSA. And so all the standards have it backwards, and they are all fragile as a result. However, going forward, you should expect to see chems being the pattern that will be used. And it's what we will consider in this talk. So here is, I'm afraid, a slightly complicated diagram of how to combine this with a one-to-one scheme. There's a lot of boxes on the screen, but if you pause for a second, you've seen all these parts before, it shouldn't be too bad. So the top line here is simply the pattern we showed on the previous slide. This is the many-to-one scheme. It takes a public key and it produces an encrypted key and the one-to-one key that you use. And at the bottom here is the simplified version of the one-to-one scheme that we showed before. And you can see that you take the message you want to send, you take the one-to-one key that was produced for you, that produces your sealed message, and obviously you need to send the encrypted version of the one-to-one key to the receiving party as well, and you can stick that on the front. So that is how we build this up into a many-to-one scheme. And in a few slides, I'll show an even more complicated scheme using this, showing how all of these parts come together. So in terms of implementation, if you are implementing this in Chromium, seek advice. I don't have a straightforward, clear API to point you, I'm afraid. Outside of Chromium, however, you can look at things like the CryptoBox API from Salt and Libsodium, or equally the same pattern of API in Golang's Xcrypto. And at this point, I'll talk about forward security because failures happen. Keys do leak. When you're doing many-to-one encryption, presumably the private key is going to be fixed for some time because the many have its counterpart. If you do leak a key, confidentiality can be retrospectively lost while authenticity cannot. Let's ponder that for a second. So if an attacker has been recording messages that they cannot decrypt, but nonetheless logging them all, and then at some point in the future, they manage to leak the many-to-one key, they can go back through their records and decrypt all of these previously undecryptable messages. So that's what I mean when I say confidentiality can be retrospectively lost. Authenticity, however, cannot be. If you received an authentic message, it was still authentic, even if in the future the key is leaked. So forward security is the property that you want to limit the amount of confidentiality that can be retrospectively lost. It is often treated as a binary property, something you have or that you do not have, but that is not true. It is a sliding scale. You measure forward security in the amount of time in which the keys remain around. So the idea here is that you want to erase keys as fast as possible so that any point in time loss of confidentiality compromises as few messages as possible. There is also a counterparty to this, which is compromise recovery. Given a point in time compromise that leaks all of the keys, if you have an ongoing protocol, how quickly do you re-establish confidentiality? But compromise recovery is a much less common concern than forward security. And towards the end of this talk, I will discuss how we implement forward security. So moving on to our last pattern, the one-to-many, one sender sending authentic messages to many receivers. This is typically called public key signing. So here is our last pattern. We combine a message with a private key and we produce a signed message. It looks very much like our simplified pattern for one-to-one encryption, right? The message is conveyed and it is slightly longer now because it contains a signature. But importantly here, we don't have confidentiality. We are assuming that this signed message gets sent out into the world. Straightforwardly, if you want to implement this in Chromium, this is the sort of the header you go look for, easy signature creator. I have an exclamation mark here because the input to this sign function is an int rather than the size t, which will be a legacy hangover. But hopefully this looks relatively intuitive from the diagram that I just explained. Okay, so now we'll discuss like how all of these can come together. And I'm going to give a simplified overview of how TLS works. So TLS is the protocol behind HTTPS. And I'm going to go back to the example that I gave right at the beginning. You buy a new Chromebook and you assume it has an authentic copy of Chrome OS. And remember how we discussed that cryptography lets you transform a confidentiality and integrity problem by moving these things through time. So this purchase of the Chromebook is the authentic transmission at one point in time. And then into the future, we want to leverage that authentic transmission to provide confidentiality and authenticity for new messages, for your emails, for your web browsing. So our goal here is to leverage that one key that we're saying, assuming that we got built into Chrome OS, and we want to set up a secure, indeed forward secure channel between Chrome OS and Google. And we're going to reference the three patterns that I've talked about in this talk to put it together. Quite a lot of steps on this slide. And I just noticed I have step 5 twice, sorry. But let's go through them slowly. Step 1, Chrome OS generates a temporary many-to-one public and private key. So our many-to-one scheme was when we had many senders sending to one party. We're going to use it in a slightly different way, but keep that in mind for now. Because in step 2, Chrome OS is going to send the public key it just generated to Google. Now think about what properties we have here, because we have none. We haven't used any one-to-one scheme. We haven't encrypted this. So this is an unprotected transmission to Google. Anyone can see this public key. It is not confidential, and it is not authentic. Google doesn't know every Chrome OS device out there when they're fresh out of the box. Google doesn't have any idea who this public key is from. It has just received it. So in step 3, we use this many-to-one public key to create the one-to-one key for the exchange. If you recall back the diagram of many-to-one encryption, the input is a public key, which Google has, and then the output is a wrapped key and the one-to-one key that has been wrapped. So Google does that process, and so it's now holding a one-to-one key, and a wrapped key. Next, Google uses its one-to-many private key to authenticate the wrapped key that it has just generated. So we're going to stick a signature on the end of that wrapped key, and then we're going to send it back to Chrome OS. Now think about what properties we have. Chrome OS knows it has an authentic message here, and it knows that because it has Google's one-to-many public key because it was built in when it was purchased. So that is the lever on which we are resting, is the authentic exchange at purchase time. So it knows that this wrapped one-to-one key came from Google, and it has the private key necessary to unwrap it. So it can unwrap, and now it has the one-to-one key, and Google has the same key. And Chrome OS knows that this key came from Google. So that was step 4. Now that we have a one-to-one key, we've previously explained how to leverage that to send authentic and confidential messages. You need to, as I reiterate, make sure that the nonce is unique each time. And since this is a straightforward situation, we can use a counter. The first message uses nonce 0, the second message uses nonce 1, and so forth. One subtlety to keep in mind here, there are 2 parties. They can't both use nonce 0 with the same key. In TLS, what is actually done is the key is derived into many different subkeys, and so the same key is not used by both parties. But if you did use the same key on both sides, it would be a classic mistake to do nonce reuse because of that. You could, for example, say all the even messages are for the client to server, the Chrome OS to Google direction, and all the odd nonces are for the other direction. That's perfectly valid. Anything that ensures that key property, that the pair of key and nonce is unique for each distinct message. Next, forward security. Once the exchange is finished, Chrome OS destroys the many-to-one private key, and both sides destroy the one-to-one key. You might have wondered in this, like, why it took so many steps to get to the point where we can exchange messages. We could simply have built into Chrome OS a many-to-one key for Google. And so Chrome OS could simply send a wrapped one-to-one key for Google and start transmitting immediately. The problem is that if Google's key ever leaked, then the confidentiality of all previous exchanges would be broken. Because we have generated this temporary key on the Chrome OS side, we can now destroy it. And that achieves forward security. Once this key has been destroyed, the confidentiality is assured. No future leak can break the confidentiality of the messages we have exchanged. Before I go on to questions, I'm just going to emphasize that if in any design you can just use TLS, i.e. HTTPS, then do so. We use cryptography a lot in Chromium, not just for TLS, in many other places. I've used a few as examples, but it is always subtle, it is always complicated. If you don't have to, don't use it. Although I hope if you do need to, I've gone through a few of the patterns and referenced a few parts of the code that will let you do so correctly. So I'm going to go look at the questions, which I have over here. If you do have questions, please put them in the Slido. They will take, I think, a little while to be approved, but they should come through quite quickly. And I'm going to go through them in order. And how are we doing for time? So I have 5 or 10 minutes to do questions. Question 1. I didn't quite understand why the sealed message in one-to-one encryption needs to be longer. How does this ensure that we can tell which messages are valid? Okay, so let's consider a simple case where the input messages are 1 byte long and only ever 1 byte long. So there are 256 possible input messages. If the sealed message was also 1 byte long, there would be 256 possible sealed messages. And so every possible sealed message would correspond to a possible input message. We could never say that a sealed message was invalid because every possible one is possible. However, if we make, say, the output 2 bytes long, then we can ensure that only 1 in 256 messages are valid, because the second byte we can set, I noted how you can do it with polynomials, you can also do it with hash functions. We set it in some way that only the other party in the one-to-one case could calculate the correct second byte. Now, obviously, 1 in 256 is not a very good forgery rejection rate. So that is why the expansion is usually 16 bytes. So our forgery rejection rate should be 1 in 2 to the 128, which is sort of a standard security level. I hope that worked. If it didn't convey correctly, please throw another question onto the queue and I'll get to it at the end. Second question. How do I know if Chromium or Chromium-based product is FIPS 140 compliant, can be used by government organizations? So FIPS 140 is a series of 3 documents and many derived documents published by NIST, which is a US government entity. Some US government organizations and some private organizations may want what is called FIPS 140 compliance. And the simple answer is that I don't believe that any build of Chromium or a Chromium-based product will be FIPS 140 compliant. Going into details, the underlying cryptographic library for most of Chromium has been FIPS 140 certified in several contexts, but it is not certified in the context of Chromium. Also, it would be a substantial amount of work to ensure that every single use of cryptographic primitives in Chromium, in fact, comes from that library. Chromium is very large, and I'm sure we have several other implementations around the place, all of which would need to be removed. So the answer, I'm afraid, is that it is not. How do I see native apps to web migrations happening? Without a decent UX redesign, the pages are bound to get heavy. I suspect that is a question for a different talk. There is a reason they don't let me design UX. It's because I'm terrible at it. I won't opine upon it here. You mentioned updates as an example. Why wouldn't they just use TLS? So in fact, our updates do use TLS, and that is a good answer. But often, and I think it is the case, but I'm not quite sure, so don't quote me on this, that our updates are additionally signed by a one-to-many key. And the reason is really security, that updates are incredibly powerful. Our core trust chain runs through software updates, and our TLS keys are necessarily on our front ends, or at least our front ends have Oracle access to them. And so we use TLS as a belt and suspenders mechanism, but additionally, because producing an update is mostly a relatively infrequent occurrence compared to terminating a TLS connection, I think we also sign them with their own keys. Another reason why you might want to do that coming into the future is as we transition to post-quantum algorithms, updates are very large. They can use schemes that are very robust, but that produce very large signatures, whereas those schemes might not be pertinent or plausible in the TLS case, which is a very high frequency intensive use. And so again, I recommend also going over TLS, but you can reasonably want to sign them with another key as well. In TLS, when a one-to-one key is thrown out, after how many messages? So let me break this down by TLS version to start off with. In practice, in fact, in all versions of TLS, one-to-one keys are not disposed of until the end of the connection. That is not required by the protocol. In TLS 1.2, you can do something called renegotiation, which is unwise. But in TLS 1.3, you can do something called key update, which rotates the one-to-one keys in a relatively sane manner. Oh, excuse me, someone's phoning me. We do not do key update in TLS 1.3. I turned it on at one point and it broke quite a lot. Some of those got fixed. I haven't gotten around to turning it on again. So in practice, the one-to-one keys are thrown out at the end of the connection. The reason I hesitate is that in TLS 1.2, there is an additional complication from something called session ticket keys, where keys that are sufficient to decrypt the connection are transmitted to the client in the clear in order to resume connections. And in the time available, I'm not going to be able to go into the details there. But the forward security of TLS 1.2 is much more complicated and is lower bounded by the session ticket encryption keys. The precise sort of handling of those in Google's production environment is not something I'm sort of going to discuss today, but there are academic papers online that have black box probed many sites, including Google, and have sort of, there's tables in these papers about when these session ticket encryption keys get rotated, and thus what the forward security window for major online services is. But the answer is now, don't use TLS 1.2, switch to TLS 1.3. TLS 1.3 does pretty much what you would want, which is dispose of everything at the end of the connection. And maybe we'll be able to turn on key update at one point and dispose of the one-to-one keys periodically within a connection. All right. With that, I have hit the 45-minute mark, and I'll pause briefly to see if there are any more questions. If not, then I think I am complete.